Alright, that explanation was getting a little bit long, and so I wanted to save the examples to a different video in case somebody wanted to jump right there. So as far as examples of putting this into practice, a majority of the homework was going to give you some polynomials and say identify if it has the vertical asymptote, oblique asymptote, or horizontal asymptote, and if so, what is it? So let's take a look at example number 1. Okay, they give us the rational function f of x is equal to 1 over x plus 3 squared. So does it have a vertical asymptote? It would have a vertical asymptote if it had a domain restriction that we couldn't get rid of, if it had something that made it undefined, and it does. It has a vertical asymptote at x equals negative 3, because if you plug negative 3 in, you get undefined. Now, the degree of the numerator is 0. The degree of the denominator is 2, right? If we were to multiply out the denominator, it would be an x squared. So we have no x's, so degree 0, over an x squared polynomial, degree 2. The degree of the bottom is bigger, or the way I worded it in the last video, the degree of the numerator is less. Anytime that happens, you have a horizontal asymptote, and that horizontal asymptote is y equals 0. Oblique asymptote, if it has none, right? So if it has a horizontal, it can't have an oblique, because the only way it has an oblique is if the degree of the numerator is 1 higher than the denominator. And so I'm just going to write none in there for emphasis, and I think you're going to actually have to choose that. If I move to a second example, okay, we're going to look at g of x being equal to 4x squared minus 5 all over x squared. Well, those x squareds can't cancel. Hopefully you realize that. They would only cancel if you could factor it out of the top, and you can't. And so we have a domain restriction that we can't get rid of. The vertical asymptote then is the line x equals 0, or the y-axis. Now, how about horizontal asymptote? It'll have a horizontal asymptote if the degree of the bottom's bigger, it's not, or if the degree of the numerator and denominator are the same, and they are. And so in this case, it's a y equals a ratio of the leading coefficients, y equals 4. Because that's what's going to win over time. Over time, then minus 5 isn't going to play much of a role. It is always going to be 4 times a number over a number. Imagine plugging in a billion squared times 4 minus 5. That minus 5 is nothing, right? It's going to be almost like 4 coming out, and so it's going to get closer and closer to 4. And again, if it has a horizontal, it cannot have an oblique. And so just writing none for emphasis there. Now, example number 3. Sorry for the hesitation there. Call this function r of x. And they have this, x cubed minus 125 all over x squared minus 9x plus 20. Now before we go to work, you want to just start looking at these functions right away, because what we want is quick analysis. So you should be looking at this function and almost crying, saying to yourself, oh, the degree of the numerator is exactly 1 higher. I got to do this crazy long division thing to find out the oblique. You should look at example 2 and be like, oh, cool, the degree of the numerator and denominator are the same, so therefore it's going to have a horizontal asymptote at 4. You should look at the first one and be like, oh, the degree of the bottom is bigger, so it's going to go to 0 over time, and know that your horizontal asymptote is 0. It's that fast sometimes. Now, the thing that stinks about number 3 is it takes some work to come out with the horizontal the oblique asymptote, apologize. But let's start with the vertical. You won't properly be able to identify the vertical unless you factor. So they're screaming something to you right here, and that is you better remember all the factoring that you've done in the past. When you knew you were taking a math science route, you should really have cared about everything that was taught to you, including all the factorizations, because they think this x cubed minus 125 is as fast as you writing x minus 5 and then square, multiply, but switch the signs, and square, because that's how it factors. they think you can totally do the bottom quick as, hey, this is a -5 and a -4, right? And so same sign, both negative, and that's what we have. We have that. Now, why is that important to see? Because you only have one vertical asymptote. Even though it has a domain restriction of 5 and 4, if vertical asymptotes are determined, let me get a red pen here off of the after simplification thing, and it's actually a better way to find the oblique too. Cut out as much as you can. Those x minus 5s are gone for us. As we graph in the next section, we don't want to forget about them. We want to remember that domain restriction, and we'll make note of it. But from a vertical asymptote point, you have 1, x equals 4. Now, the degree of the numerator is bigger than the degree of the denominator. Therefore, it has no horizontal asymptote. And because it's bigger by 1, we do have an oblique asymptote, and I can't write down what that is. What I need to do is take x minus 4 into x squared plus 5x plus 25. Now, if you've forgotten how to factor differences of cubes or sums of cubes, well, you can pull out an old intermediate algebra textbook, usually is where it's taught. Or you can look it up online, but it's relatively easy. It should be a memory jog for you. So now we're just doing long division like we did in Algebra 1, Chapter 6, also Algebra 2, about the same place, honestly. So x going into x squared once as an x, and I get an x squared minus 4x. Remember to subtract, I'll do that in red. Subtract, subtract, and we end up subtracting, because if you get this part wrong, I'll mark you wrong, the computer will mark you wrong, because it's a 9x that we're looking at. So we need an x to go into a 9x, so I need a plus 9. So if you have a -1 or 1 or something in there, it's not going to work. You got to be able to do your subtractions well. And we get a 9x minus 36. And here, you don't care. We're not after the remainder, we're after what it looks like. For all intensive purposes, for large values of x, it's going to look like x plus 9. So y equals x plus 9 is the equation of the line that it follows. An oblique asymptote is a line. Just like in the last video, it was the line 2x. In this case, it's the line x plus 9, doing the long division that we practiced with twice, including learning synthetic division in our last class, so because we knew we were going to do it so often. Let's look at one last example, because they're all very similar. Example number 4. And I tried to pick them where they were interesting enough, so hopefully with the others you will recognize the similarities in that. So I was just looking for things where you might be daunted, because we might as well do those together. Same thing I would have done if I had you in class. So what's the first step to do? The first step is say, oh, this is so nice, Wayne. This is so nice, Professor Jensen, because look at that. The degree of the polynomials are the same. I'll worry about the vertical asymptotes in a minute, but right now, Professor Jensen, you know what I know? It has a horizontal asymptote of y equals 5/3, no matter what else happens. It's got to be that. And oblique asymptote, I don't have to do that long division. The oblique asymptote is none, right? Because if it has a horizontal, it can't have an oblique. So let's talk about the vertical asymptote. Only way to do that is to be able to factor. So you're looking for however you want to go about factoring this. Hey, I would say, hey, what are the factors of 60 that subtract to be 28, potentially? Or I could look at the bottom. Bottom's actually easier. Factors of 18 that subtract to be 17. And I'd know that it's a 3x that needs to hit a 6. And so however you factor, there's no magic. It's whatever you gravitated to in your whole thing. I've seen people do little chart things, and you just want to be fast because they're thinking that that's not the long part of the problem. And you'll get fast as you allow yourself to practice. So it's a 6 and a 1 and an x, because why does that work? Because 3 times 6 is 18. And so I want that to be negative plus an opposite would bring me down to 17 negative. You could use that knowledge up here. Well, maybe. So here we're looking for factors of 60 that subtract to be 28. All right, that's going to be a 5x and an x, and it's going to be a 30 and a 2. It's going to be a positive 30 and a negative 2 coming through. Oh, I miswrote that because that was not going to have the desired effect that they wanted. I miswrote it when I first started. They had a minus in the middle there, which means it's a negative 30 and a positive 2. So why is that important? Because they wanted one more time to illustrate that although the domain, so the domain still would be the set of all x's such that x does not equal negative 1/3 and x does not equal 6. Don't rule out the 6 only because it crosses out. It does cross out for how the graph behaves. It just has a hole at 6. And so we're looking for only one vertical asymptote. We only have one. And that vertical asymptote is at x equals negative 1/3 if we solve that for x. That's what's going to make that thing 0. And so we're done, right? We're just getting practice identifying these. Next week we'll go ahead and graph them and get prepared for the exam. All right, enjoy this work with rational exponents, or not exponents, rational functions, and then contact me if there's questions or concerns by either coming to the support hours like many are already doing, or sending me emails saying, hey Jensen, I don't know how to do this one, and I'll help you through it.